Welcome to another video. Let's solve this British Mathematics Olympiad problem from 1995. It's a beautiful problem because of all the nuances that are involved in solving it. So it says if A, B, and C are natural numbers, that is numbers you can count on your fingers, which will be 1, 2, 3, 4, 5. There's no zero involved, and obviously this can be zero, so we cannot have zero because you have fractions there. Natural numbers, we're supposed to solve this equation. It's 1 plus the reciprocal of A times 1 plus the reciprocal of B plus 1 plus the reciprocal of C is equal to 2. See, the equality makes life a lot easier because then we can create restrictions. Okay. Straight away, there's something you have to see, that none of these letters can be 1 because, you see, they're all positive. So it means this factor on the left-hand side is greater than 1 because this is 1 plus something. This can never be 0 because the only way this will be 0 is if A is infinity, but infinity is not a natural number. So there will always be something greater than 1 here. But if this A is 1, then this becomes 1 plus 1, which gives us 2. So 2 times anything greater than 1 is bigger than 2, which already defeats this equation. So it means none of these A, B, C can be 1. So now we know that as part of the options we're looking for, you cannot consider 1 as an option. So we have to start from 2 or 3 or 4 or 5 or 6 or forever. Just keep going. Just don't get to infinity. Let's get into the video. Now that we have eliminated 1, there's something else I want you to consider every time you take a problem like this. You want to see if it is possible, because this is a symmetric equation. If you switch the positions of A, B, or C, it doesn't matter. It will still be the same equation that you have, right? And whenever that happens, the first factor you want to consider, is it possible that A is equal to B and it's equal to C? Because for symmetric equations, that sometimes happens, frequently even happens. So let's try to see if we can replace B and C with just A and see what we're going to get. So let's just say, suppose A equals B equals C. That's the first move I want to make now that I've eliminated x equals 1. We know x equals 1 is not an option. Okay, I just said that mentally. Verbally, I should have written it. So now, what do we have? So instead of writing this 3 times, we're going to write 1 plus 1 over A cubed. This times this times this is going to be equal to 2. And what does that mean? It means that 1 plus 1 over A will be equal to the cube root of 2. So that means that 1 over A, let's write it here. So that means 1 over A equals cube root of 2 minus 1, which implies A equals 1 over the cube root of 2 minus 1. Remember, we're told that A is a natural number. Okay? This is not a natural number. Therefore, because we're not getting natural numbers when all of them are equal, this condition that we supposed at the beginning is not true. So that means A is not equal to B and we don't have a situation where all 3 of them are equal. It's possible that 2 are equal, but not all 3 are equal. Okay, so our supposition does not hold. So what's the next thing we want to consider? Well, you want to go back to the equation and start thinking about the nature of the problem. What's going on? You see, as A gets bigger, this factor gets smaller. Remember, as the denominator of a fraction gets bigger, the fraction gets smaller. So if you started with 1 plus 0.5, now you change this 0.5, this 2 here, you change it to, say, 10. It becomes 1 plus 0.1. So it's now much smaller. Change it to 100, 1.0.01. So it's getting smaller and smaller and smaller. And this also is getting smaller as b gets bigger. And this is getting smaller as b gets bigger. So you can also see the future, that there's going to come a point where you cannot keep increasing these numbers. There just has to be a limit. We know the lower limit. You cannot go below 2 because 1 is not part of it. We already said that from the beginning. But there's got to be a maximum for either of them. Now, because there are 3 variables, you don't want to just generalize. Make your life easy by assuming that one of them is less than the other. So let's make this assumption. Without loss of generality, let A be less than or equal to B, and let B be less than or equal to C. This is going to save us, because what we're saying now is that A is the smallest of them and C is the biggest. Since they're not all the same, so it's possible that A and B are the same. It is possible that B and C are the same, but only 2 of them can be the same. These 2 can be the same, or this 2 can be the same, and that's going to save us, because now there's a fact. The smaller the denominator, the bigger the factor, right? So if this is 2, and this is 3, and this is 4, then this is the biggest, right? Okay, so we're going to use that now. We know, note, by this assumption, that this thing here, 1 plus 1 over A times 1 plus 1 over B times 1 plus 1 over C is equal to 2, but we know that this has to be less than or equal to, if I'm only repeating this one, the one I said is the biggest one, which is 1 plus 1 over A. I'm repeating it 3 times. So the biggest factor, I'm using it to replace these 2, but because I'm using big to replace small, small, then this left-hand side is definitely less than this one. This guy is the biggest guy. And this is equal to 2. So I have established an inequality that 2 is less than this. Now, if I take the cube root, just like what I did before, what do I have? I take the cube root of 2 is less than or equal to 1 plus 1 over A. So I have 1 over A. So that means if I flip, A is less than or equal to 1 over the cube root of 2 minus 1. Now, I could have done this with calculus, but I didn't want to bring calculus into this because I thought this was just Diophantine equations, and, well, I could have used calculus for it, but I know what I'm doing, okay? Because I know the cube root of 2 to be 0.26. Okay, square root of 2, 1.41. Cube root of 2, 1.26 rather, not 0.26, 1.26. So I know that A is less than or equal to 1 over 1.26 minus 1, which is equal to 1 over 0.26. Hey, A is less than or equal to 100 over 26. Now tell me, what is 100 over 26? How many times will 26 divide 100? Not up to 4. So it is more like 3.8 or 3.9. So A is less than or equal to let's just say 3.8. Remember, A is a natural number. So the natural numbers that are less than 3.8 but greater than 1, which we already eliminated, which I should have written, are 2 and 3. So A must be equal to 2 or 3. These are the 2 possible values of A, since A is the smallest. It's either 2 or 3. It cannot be 4. It cannot be 5 because of just this tiny little math that I did. Okay? Okay. Now, you would ask me, what if I don't know the cube root of 2? Well, I'll tell you to just try the numbers. And if you keep trying numbers, say you plug in here, so you plug in 2, it's going to work. You plug in 3, it's going to work. See, 2 is supposed to be less than it, right? But by the time you plug in a number greater than 3, this equation will no longer be true. And then you go, okay, now I know. But I just needed to show it. So now we have seen the 2 possible values of A. So all the answers we're going to get will have A as 2 or A as 3. Let A be equal to 2. So this is the very first one we're going to do. If A is equal to 2, let's go back to the original equation. This is going to be 1 plus 1/2, right? So this we're going to have is equal to 2. Okay, so see in the denominator I have 2bc. Multiply both sides by 2bc, and then I'm going to distribute this. I'm just trying to save space and time. If you distribute the top, this is what you're going to get. Nice. I'll put one more line here. Now, if I clean everything up, if I move everything to the side, 4bc minus 3bc is going to give me bc. So I'm going to get bc minus 3b minus 3c minus 3 is equal to 0. Nice. Now, my intention is to be able to solve this equation for natural numbers. It is always easy to solve this. Okay, one equation, because you're using natural numbers, no decimals, no irrational numbers, it's always easy. What you're going to do is see if you can factor. So we want to try and factor this. What's common to this and this? We're going to have b, and we'll be left with c minus 3. What's common to this and this? We're going to factor out 3. We'll be left with c plus 1. That's not good. See, here we have c minus 3. Here we're going to be left with c plus 1 if we factor out the negative 3. We don't want c plus 1. We want c minus 3. What can I do so that what I have here is going to end up being minus 3 after I factor out minus 3? It has to be a positive number that's divisible by 3. So that has to be positive 9. Okay? So what would I do to minus 3 to make it positive 9? I need to add 12 to it. It's because I need to get c minus 3. So if I add 12 to this, I need to add 12 to the other side. So I can go here and say, and I'm going to get 12 on this side. You see what I'm saying? I added 12 to both sides. Now I can factor. If what's common here, it's b. b into c minus 3. What's common here? Minus 3. c minus 3 equals 12. So here I have b minus 3, c minus 3 is equal to 12. These are natural numbers. So it's the product of two natural numbers, two integers, that's going to give me 12. So you just need to factor 12 into the possible combinations. Now, let's go back to this assumption. We said b is less than c. It's less than c or equal to c. So when we're taking the smaller factors of 12, they have to go to b. The bigger factors will have to go to c. So we can say from here, look, the possible options we have are 1 times 12. We also have 2 times 6. We also have 3 times 4. Those are the possible combinations that we can have for these three, where b minus 3 is going to be 1. So I'm just going to finish it this way. So b minus 3 is going to be 1, which means b has to be 4, right? So which implies the solutions, b is going to be 4. And what will c be? C is going to be, this is 12. If something minus 3 is 12, then that thing is 15. Nice. Let me make a table here so it's clear. If we use this one, it implies something minus 3 is 2. That thing must be 5. and this has to be 9. And here, something minus 3 is 3, that has to be 6, and this has to be 7. So, remember, everything we did is based on the assumption that A is equal to 2. So we have one set of solutions which I can write. You know what I'm going to do? I'm going to erase the board here. So the solutions A, B, and C are going to be that A equals 2, you have 2, B equals the first one, B equals 4, and C equals 15. So this is the first set of solution. I also have another set. B is 5, 2, 5, 9. And the third one is going to be 2, 6, 7. Okay, now these solutions that I just got are based on the assumption that A is the smallest one. It's possible that A is not the smallest one. Remember, we narrowed things down just to make us find answers. We can actually switch these because remember, the original problem is symmetric. So now it's either this is a set of solutions or we can permutate this. If you do the permutation, this is 3 things. So you want to do 3 factorial. So there are 3 factorial arrangements of this. I can write them out. It's either 3, 4, 15 or 3, 15, 4. I mean, 2, 4, 15 or 2, 15, 4 or 4, 2, 15 or 4, 15, 2 or 15, 4, 2 or 15, 2, 4. Those are the 6 possible combinations. Okay, but I don't want to write it. I'm going to write it. I have written out all the possible combinations. And how many do we have? We got 3 by 6. We got 18 solutions already. Wow, we're so smart. Okay, now let's do the second condition when A is equal to 3. So when A equals 3, what we're going to do is say that 1 plus 1 over 3, which is going to be 4 over 3. I'm going to do shorthand now. Into, you have B plus 1 over B times C plus 1 over C is equal to 2. So considering what I have here, at the end of the day, this is what I'm going to have. I'm going to have, because 2 will divide this 2, and then this 3BC goes that way, I'm going to end up with 2BC plus 2B plus 2C plus 2 equals 3BC. Okay, nice. Now, like we did before, we're going to drag everything to one side. We end up with BC minus 2B minus 2C minus 2 equals 0. And like we did, remember, B is common to both sides. So we're going to have C minus 2 left. If we factor out negative 2, we're going to end up with C plus 1. But we don't want C plus 1, we want C minus 2. So in order to retain the negative sign here, this has to turn into a positive, but a number divisible by 2, which is going to be positive 4. How do you make minus 2 positive 4? You add 6 to it. So I'm going to add 6 to this side, and I'm going to add 6 to this side. So I'll end up with BC minus 2B minus 2C plus 4. Is equal to 6. I've added 6 to both sides here. So now I can factor. B is common, so I have C minus 2 into C minus 2 equals 6. So I end up with B minus 2 times C minus 2 is equal to 6. So all I have to do is ask myself, what are the integer factors of 6? Distribute this way. Remember our assumption that B is less than C. So I'm going to do 1 times 6. The same thing, I'm going to do 2 times 3. So I'm ascribing the smaller values to the B. What does that give me? It tells me that solutions, the possible solutions I have now are, let's write B, C, like I did before. So something minus 2 gives me 1, that thing is 3. Something minus 2 gives me 6, that thing is 8. Something minus 2 gives me 2, that thing gives me 4. And something minus 2 gives me 3, that thing is 5. So our solutions are 3, 3, 8, and 3, 4, 5. Oh, this Pythagorean triple is here. Nice. Okay, so these are the two possible solutions from this side. But don't forget they have their permutations. Now, this one, because there's a repeat, it's going to be 3 factorial divided by 2 factorial, which is 6 divided by 2, which is 3. So only 3 different combinations will come from this. In this case, we're going to have 6 different combinations, which is 3 factorial. 3, 4, and 5, 4, 3. So if we count the total number of solutions to this Olympiad problem, it is 27. We got 18, and we just generated 9, 27 in total. Never stop learning. Those who stop learning, stop living. Bye-bye.